Hello, everyone, and welcome to the final event of the fourth day of HTEC Days 2025 conference. This is a unique event in this year's conference. So far, we've only had internal presentations and presentations by members of our teams from different business units. This is a presentation by our partner company, AMD. The title of the presentation is Advancing AI in Video Games with AMD Schola, and the presenters for today will be Alexander Cann, member of technical staff at AMD. Alex is a lead developer at Schola, and his research interests cover deep neural networks, reinforcement learning, and the intersection of AI and games. Also with us, we have Mehdi Saeedi, principal member of technical staff at AMD. Mehdi is the AI lead at Schola. He's the lead for machine learning-based non-playable characters in video games. His research interests include reinforcement learning, deep learning, and the intersection of graphics and AI. Finally, with us is Gabor Sines, Senior Fellow Engineer at AMD. Gabor is a leader in research and development within the realms of machine learning and graphics, while also collaborating with external partners on AMD artificial intelligence and machine learning solutions. Gabor will also be the moderator for today's session and the Q&A part of the presentation. Without further ado, I will turn over the mic to our presenters, and let's all enjoy this exciting presentation.
Thanks, Ismail. So the topic of the presentation is, as Ismail said, advancing AI in video games with AMD Schola. To cover that, I just want to highlight one important point about video games. So the reason that actually we want to highlight video games, because video games, generally speaking, are affecting many people's life, right? Some people play the game, some people watch the streams, and you kind of know actually at least one person that is kind of interacting with video games. That's basically one side of the story. The other side of the story is video games is a mixture of technology and art. And because of that, it's basically considered as an excellent tool for fostering creativity. And that's very important to know. With that, I'm going to open basically the talk and talk about what we are going to cover in this presentation. We are going to talk about how AI in general can be used in video games, and which form of AI can be used. And then I'm going to cover briefly about this traditional AI in video games. And then I'm going to jump into reinforcement learning, explain it a little bit further. And then I'm going to give it to my colleague, Alex, to take over and talk about AMD Schola. And we will see some examples. And at the end, I'm going to take it back, talk about digital twins, and then we will conclude the presentation. Now let's talk about AI in video games. As you can imagine, AI can be used in different ways in video games. It can be used to enrich non-playable characters. It can be used to enhance the content in the video, right? For example, using procedural content generation for enhancing graphics, or it can be used for testing games, for adjusting the difficulty when you play the game, or it can be to, let's say, enhance the interactivity inside the game, right? By improving the voice and dialogue system that you have in the game. I guess actually the question is where we are going to investigate and invest our time further. For this talk, we are going to focus on the first part, which is non-playable characters. Non-playable characters, or NPCs in short, are the ones that actually are in the scene to enhance the experience of the game, but they are not controlled by the game player. So for example, if you have an NPC and you're going to shoot the NPC, that NPC is something that we are interested to enhance its behavior. Now, focusing on non-playable characters, if you ask, let's say, Copilot, which form of AI can be used in video games, so you're going to see a lot of different ways, right? Starting from the traditional finite state machines or FSMs, going into pathfinding algorithms, decision trees, neural networks, and all these things. I'm going to briefly cover those. And then, as you can see, reinforcement learning is number 7, and we are going to step into that and then take it over. Let's a little bit focus on the traditional AIs in video games. The reason that actually I have AI here is because if you look for AI in video games, you're going to see these type of things that I have here. Traditionally, basically anything smart in video games called AI. It can be finite state machines or it can be navigation mesh, right? As we move towards the real AI, we can call it, for example, ML-driven NPCs. And I just wanted to highlight the term here. Now let's focus on the first picture that I have here. Let's assume that we have Alice and Bob, and they want to, let's say, find each other. And the problem that we are going to have here is a navigation problem. There are many, many different ways for Alice to reach to Bob. The question is how to basically find this road. And obviously, you can do the traditional way, which is a graph-based approach. They call it navigation mesh or nav mesh, or you can use AI for Alice to reach Bob. And then the question is, which one is better, right? For example, avoiding obstacles, having a diverse behavior, having a human-like behavior. These things are the things that are important for coming with basically a new interesting way of navigation when you are facing navigation in video games. On the other side of the screen, I have this FSM. FSM or finite state machine is the traditional approach to control the decision makings in video games. Let's assume that you have a patrol NPC. The NPC is going to chase or attack. Considering the different conditions that you have in game, for example, player is inside or player lost the sight, or it's if the player is close enough to the NPC, and so on and so forth, you can have different actions. And that's the way that people usually control NPCs in video games. Now with that, I'm going to get into reinforcement learning. But before talking about the formal definition of reinforcement learning, I wanted to highlight something from our real life. Let's assume that you are going to learn to ride a bike. There are different ways to do it, right? Let's see actually which way is going to help us the most. So you can use the traditional teacher-student approach. You can sit in a class and the teacher is going to explain that actually you have two wheels, right? It's going to be hard for you to stay up. You need to do this and that. So that's basically one way. I'm not sure if you're going to learn something from this way of learning riding a bike. The other way is basically not having a teacher, but sitting in a class and another peer, right? Somebody that tried it, try it and you just watch it. By watching somebody is learning, right? Is it going to be helpful? Maybe, but not much. The question actually that I wanted to highlight is for some particular type of learning, the traditional supervised learning or the traditional way of let's say teacher-student learning is not going to be useful. That's why reinforcement learning is something very important for some particular scenarios. In our case, for riding a bike, you can start from basically something as small. When you learn it, you move to another lesson, which we'll call it lesson-based learning in reinforcement learning. So that's important. And with this reinforced behavior, you're going to learn how to ride a bike, and eventually you're going to be good at it. Now that we understand reinforcement learning is a concept that is very important in some particular case of learnings, I'm going to try to conceptualize it, right? In reinforcement learning, the entity that is learning, we call it agent. So here in our case, you are going to be an agent. And then we have an environment that the agent is learning inside this. In our case, the environment is going to be the bike itself, the floor that you are riding, the noise that you are hearing. All of these are going to basically be inside this environment. And then you are going to observe using, let's say, your ears, your eyes, your hands, and everything, right? And then based on whatever you are observing, you are going to take some action. And then these actions are going to be paddle more, or I don't know, put your feet on the floor, and so on and so forth. So agent, observation, environment, and action are the most important part that I want to highlight in the next following us slide. I also have a reward. In reinforcement learning, there is a definition of reward that basically highlights what's good and what's bad. In sometimes it's basically not an external reward. For example, if a kid is trying to ride a bike, maybe the kid doesn't understand the benefit of riding the bike. And in that case, we are going to have some external, let's say, reward, like parents clapping or that kind of thing to encourage this learning. On the other hand, let's say you understand that actually you need to learn, and then it's going to be something internal, and you see you are moving from A to B, and you are learning, and you are keeping on the bike for a longer time, and that's kind of reward for you. So there are many different definitions of reward that you can imagine, but it's a very important concept in the paradigm of reinforcement learning. Now with that, let's talk about some real concepts. Now, you already know the definition of agent and environment. And I would like to highlight the definition of interaction here. Agent is going to interact with the environment. And by interaction, we are going to talk about what agent is going to see or observe in the environment. We call it a state formally. And a state can be anything that the agent observe in the environment. In our case, it can be the type of road that we are in, and the thing that we are hearing, everything that is related to the interaction of agent and environment. You are seeing here S with index T. Basically, it means that at time step T, you are going to, or agent is going to observe something from the environment. Then we have an action in the same step T based on the observation that the agent saw. Now the agent is going to take an action in this environment. And then we are going to see a new state, and then we are going to see if it was good or bad in terms of the reward. And then we will see the next state in the next step. So basically, agent is in the environment doing something, observing the outcome of it, and then doing another thing, and then observing the outcome of it. And this is a closed loop, and it's going to take for some time. And after this some time, with the feedback that the agent gets from the environment, we believe, or we would like to have this agent to learn something that is useful from, let's say, design perspective. When the agent interacts with the environment and does all these actions and collect observations and everything, the agent is going to equipped with a trained model, right? In reinforcement learning, it is called policy. And policy is going to govern the action that we take conditioned on the state that we are. So it's going to be in a state T, we are going to take action A, and that's is going to be governed by policy. At the beginning, it's going to be random. There is no policy, good policy, but as the agent learns, it's going to be something interesting. For example, in the riding a bike example, the policy is going to be something in your brain. You're going to see, I don't know, maybe now it's time for just paddle. Now it's time for put your feet on the ground, or you balance yourself. So these are the actions, right? As you learn more, these actions are going to change, and this is the policy that you're going to be equipped with. there is, we talked about reward, right? But in reinforcement learning, it's important to understand that we are not just capitalizing the immediate reward. For example, um, assuming that your journey, let's say navigation from A to B, is going to take many steps. We are not just interested in the step that follows the current step. We are interested to see how we can maximize the total reward that we get over this journey. So it's an important to understand that there is a horizon, and over this horizon, we want to maximize the total reward. Otherwise, if everything is greedy and we just optimize the reward that is going to follow the current step, then it's going to be a greedy policy, and it's not going to be a good policy. So we want to maximize this reward. However, if you just add the current reward plus the reward at the next step plus the reward at the 2 steps from here, then what's going to happen is you are going to explode in the total reward, because let's assume that you are going to give reward 1, right? And then if you add all these in a horizon steps that you have in the horizon, and let's assume that your horizon is going to be big, then you're going to have a lot of rewards to add them together. To avoid this, in reinforcement learning, we have this concept of you're going to have this accumulated reward, but not basically using the same um, proportion, right? So you're going to have a fraction, and this is basically the concept that you have here in this sigma. You are going to have gamma to the power of a step times r for that step. So for example, in the next step, you consider everything for this reward, but in 2 steps from now, you're going to get a little less fraction, and so on and so forth. So you're going to pay attention to the next step more than other steps, but you are not going to ignore other steps. With that, let's consider a few examples. Let's assume that there is a cart, and we have a pendulum in this cart, and we have basically a rod, and we have a mass, and we want to keep the cart in a way that this pendulum is going to stay upright. For this particular case, which is a classic decision-making problem, right? You can use the classic control closed-loop control system that we all learned in our textbooks, right? In our case, in reinforcement learning case, we want to solve it with the condition that I said, and I would like to highlight a few things here. So first of all, you're going to have 2 actions. You're going to push the cart to the left or push the cart to the right. You are going to observe this angle that you have here, the cart position, the cart velocity, this pole angle, and this pole angular velocity. So these are basically the observation that you see. And based on that, you're going to see, okay, so let's assume that the angle is this much, then it means that you need to push the cart to the left, and so on and so forth. We are looking forward to see how we can train a policy to behave in a way that it should behave. However, there are some terminal conditions, right? For example, if the pole angle is greater than, let's say, a threshold, then you cannot fix it. You cannot just try to push the car to the left or to the right, and at the end, it's going to basically fall off. So there are some terminal conditions like cart position, pole angle, and one thing that I would like here is basically the episode length, which basically means you kept doing whatever you are doing for a long time and you want to start fresh. And in that case, we are going to say the episode length is greater than a threshold, and in that case, we basically stop it. So as you can imagine, as an engineer or as a scientist, when you face basically a problem in reinforcement learning, you need to come with observations, actions, rewards, terminal state, and then you are going to benefit from a reinforcement learning algorithm to train this. Now I'm going to dig deeper and show you a few different things. Let's assume that we are facing a navigation problem. In this navigation problem, you have a very small grid. Let's assume that it's a 4x3 grid. You have some terminal conditions or terminal states, which basically means wherever you are, you are going to take these 4 actions that I have here to get to the closest, let's say, black square. I guess actually let's just go a little bit high level. Let's assume that you are in a road and this black squares are the coffee shop. And for you, you just want to reach to the closest coffee shop. How you're going to do that? And you can basically take all these actions to try to get to a coffee shop. And the reward per step is -1. So basically, if you can get to the coffee shop fast or faster, then the total reward that you get is going to be maximized, right? For example, considering the situation that you go up, then go down, then do this loop, and then eventually you get to the loop, you're going to have a lot of negative reward versus if you just go up and then get to the coffee shop. So we are interested to learn that policy, and we want to see how it is possible to learn that. First of all, let's talk about 2 possible scenarios, which is one of them is a random policy. So in this random policy, as you can see, and at each square, you have a possible action to go left, right, up, and down, all of them possible with the same probability. That's basically a random policy, which is not a good policy. However, if you train the agent to do something good, then we are going to end up with an optimal policy. And in this situation, if you are in this square, then you just go up. If you are in this square, you just go down. And so on. So for each square, there is a set of actions that are optimal. For example, if you are in grid cell 2x2, then you can just either go up, down, left, and up, left, right, and all of them are possible.
Mehdi, it seems to me that we lost your audio.
Can you hear me?
Yes, we can hear you now.
Okay. Okay, thank you. So after that, now I'm going to show you something that actually we used Schola to train agents. And in this situation, you can see actually we increased the grid size to be 9x9. And then when we do the training for each episode of the training, we created a random grid. And these cells, these black cells are basically placed in a random way. And now the agent needs to learn how to get to the terminal state based on that. As you can see, at first, at the start of the training, there is no hope, right? The agent is just behaving randomly to interact with the environment. But after some time, let's say we are now during the training and it's fast speed. In that case, you see actually the agent is interacting and we are seeing a lot of different conditions in the environment. And if we continue, you're going to see after, let's say, 100K steps, now the agent kind of know what to do. So you see actually the agents is moving towards the end goal. It's a not optimal path, but the agent is learning, right? And sometimes actually it just achieve what it needs to be achieved, and sometimes it's just a new condition for the agent, and the agent needs to learn more. Now, if you just go, let's say, after 1 million step, what's going to happen is if we have basically a generic 9x9 grid, 1 million step is good, but not perfect. And in that case, you see actually, for example, if you are here, there is a probability, higher probability to go this way. And then, so you see there is a good path from this location to a terminal location. However, sometimes actually it's not perfect. And if you just use one specific grid with predefined squares for terminal states, in that case, the agent actually is acting perfectly. So for example, here, the agent just moved 2 steps to the left. If we are here, the agent knows that it should move to the left. And when we are far, so there is a probability to go up, but it's going to be similar to probability to go to the left, and so on and so forth. So the agent eventually learns how to react. And based on that, I'm going to give it to my colleague Alex to continue the discussion.
Okay, thanks, Mehdi. So I'm going to be talking about AMD Schola in more detail. So AMD Schola, or School in Latin, is a toolkit for bringing the power of reinforcement learning to Unreal Engine, which is a popular framework for developing games, as well as for enabling the use of Unreal Engine for reinforcement learning research. So from here, I'm going to talk briefly about Unreal Engine. Then I'm going to walk through how Schola works and how you would use it. And then finally, I'll wrap up by going through an example environment built with Schola in more depth. So a game engine is a framework or application to assist in the development of games. One of the most popular is Unreal Engine from Epic Games, which you may know from the very popular game Fortnite. So it provides quite a few features for developers to kind of build games. So some of the kind of key ones I'm going to highlight are visual coding language called Blueprints, and there'll be more on this later as I'm going to show some Blueprint code. Tools for animations, tools for simulating physics, some traditional AI systems. So as May talked about before, state machines, behavioral trees, as well as other tools. So I'm going to move back to Schola from here. Yeah, move back to Schola from here. And to start, I'm going to talk about like how you build an environment with Schola, and then basically how we go from there for training. Right, so you start in Unreal Engine, you're going to construct an environment. Right, basically your game, you're going to put your NPCs in it, and you're going to have your logic. And what Schola is going to do is it's going to take that environment and it's going to translate it into APIs compatible with these open source reinforcement learning libraries written in Python. So the first one I'm talking about is Gymnasium, which is kind of a de facto standard for reinforcement learning libraries, and is widely supported, but doesn't really provide tools for training and other things. It's just for environments, whereas Stable Baselines 3 and ROLib are more specialized, but they also provide algorithms, model architectures, tools for importing, exporting, things for wrapping your environments to do different things, to do different capabilities and kind of tricks and stuff like that, right? So moving to inference, right? We have our trained model. We trained it with SB3 or RLib, or we took Gym and then used another framework to train it. And we're going to export it to ONNX, or Open Neural Network Exchange format, which is another widely supported tool for representing neural networks or machine learning models. And then what you're going to do is once it's exported with Schola, you can then load it up in Unreal Engine into your environment that you built, and then run it inside your game, reusing kind of the environment for training. All right, and that way, because everything is the same, it'll basically perform as it did during training or better, for a few reasons relating to how reinforcement learning works. So from there, I'm kind of going to segue into a high-level overview of how you actually would build something with Schola, right? Because now we have this picture of the various parts, right? And to start, I'm going to return back to this diagram Mehdi presented, right? So the high-level kind of flow or system of a reinforcement learning application, we start from some state of the environment, right? It goes to the agent, which generates the next action. From the next action, it goes back to the environment, and then using that initial state in the action, we get a new state and a reward, and then so on and so forth. We get a new action from the new state, so et cetera, right? So that leaves us with a few key concepts. And what I'm going to do is I'm going to basically relate those back to kind of 5 key APIs in Schola that'll explain how you would use it to build a reinforcement learning system. Right. So the first one I'm going to talk about is actions. And this corresponds to the concept of actuators in Schola, right? So an actuator is essentially given to the developer as an interface that requires two things to be defined. One of them is the definition of the action, right? So this could be binary, like yes or no. It could be categorical, left, right, forward, backwards, or it could be floating points, as in 45.6 degrees, right? And then also the function that generates the action, so which chooses between forward, left, right, center, etc. Right? So then here on this slide, you'll see a couple of examples of actuators. Top right, you'll find the teleportation actuator, right? That's moving the agent in the Y dimension and just sort of teleporting it. Then you'll find a movement input actuator, which is moving the agent on the forward and left-right axes. And this is basically simulating a joystick input, right? And then the last one is a rotation actuator that rotates the agent. And this one specifically is on the pitch and roll dimensions. So then similarly for state, we have the concept of an observer, which is essentially analogous, right? We have this API, one function for definition, one function for actually collecting. And then similarly, categorical, binary, and floating point are the three kind of types. And then once again, some examples. We have a rotation position sensor that gets the X, Y, Z coordinates of the agent. We have a raycast sensor that fires out some rays, and this is kind of equivalent to a LiDAR. You think of like a self-driving car application, right? This one shoots at 36 rays on a 180-degree semicircle, and you can see it's detecting that there is something in front of the agent. And then finally, one here for a rotation sensor that's detecting the pitch, yaw, and roll of the agent. And then we provide a few more of both actuators and observers. And these ones are provided for example. And this is to help a developer get a sense for how to develop with them. And also, if you want to quickly scaffold and build out an application to test it out, you don't need to actually build new ones. You can just kind of drag and drop these parts onto an NPC. So the next thing I'm going to talk about is the trainer, which handles the part of taking the actions and converting the observations that come out of the observers and then sending them off to Python to get back some actions that are then taken in the environment so we can get the reward and the next state. And it doesn't quite line up with the policy because the trainer is also responsible for the reward. And here, right, because it doesn't do the inference during training in Unreal, it sends the observations to Python, where Stable Baselines 3 and RLib or another framework provides kind of the actual machine learning computation of what the next action is. And the trainer is more so the glue that holds it all together, right? So it provides some utility functions for reset trainer. When your episode ends, right, maybe you truncated because it took 500 steps or 200 steps in the case of the cart pole example from earlier. Some tools for extra events when you finish an episode. Some utilities for basically sending metadata back and forth from Unreal to Python. But then the real meat of the class comes in the compute reward and compute status functions. In compute reward, you get the reward, which is not too surprising, all things considered. And this is where I'm going to introduce how to read blueprint code. So this is the aforementioned visual scripting language. And basically, both of these pictures represent two functions, right? So when you're reading blueprint code, the white lines represent like a thread of execution. So this is a function compute reward. It starts at the square labeled compute reward and goes to the return node. For other pins, you read backwards to figure out what's happening. So it goes to return, and then it goes to the make literal float, where it just makes a floating point value with the value 0.02, and then returns that. On the other hand, we have the compute status, which is what tells us when the episode is completed, truncated, or still running. And this one, same thing, goes backwards. However, it converts a Boolean value to a enum first before returning it. So if we're doing inference, right, and let's say we're in a game, we don't want to be sending things to Python because that invokes extra headaches. So we have this idea of a policy that runs the inference all in Unreal using our Onyx model. So on the top here, you can see a picture of an Onyx model exported with Schola. So it has several inputs, right? The first one represents that ray or LiDAR sensor we saw before, detecting a few things on a specific channel. And then it also has some other sensors that are basically have size 4, detecting position and distance to some other objects in the scene. And then it also handles a state input-output that here is just kind of an empty input-output. And that's for managing things like recursive neural networks or long short-term memory that uses a state to kind of let the agent recall what happened in previous steps. So it's not, the agent is no longer operating solely on the current state. It's operating on its own processing of previous states as well. So the next thing I'm going to talk about is the environment. And this basically represents the rest of the logic for handling the environment, right? So here you can see a picture from an environment for Pong, right? We have a ball, we have some walls, and then later the NPCs will be added in when the game is created, right? And this object will have a few responsibilities, as well as some utility functions, right? So it has tools for initializing the environment, setting a random seed, and this is commonly used for making training repeatable, right? Because the process is used to train these models, it's frequently stochastic gradient descent, is randomized, and as well as it's often useful to randomize the environment because otherwise agents will memorize the structure of the environment. If you want to basically redo some results, you need to have a seed, so that's what that does, as well as for registering agents and basically denoting which NPCs should be controlled by Schola and which are maybe not responsible for training or potentially are already trained agents we're using as opponents for agents we want to train. Right, so I'm going to once again highlight some blueprint code. And this is the reset environment. An event is really just a function with no return. So it can be read exactly the same way. And this is just a sample kind of contrived reset function for Pong. You know, put the Pong agents / paddles back where they should be at the center of each of the sides, and then put the ball back in the center, right? And then initialize environment does something similar, but it's just called once to do setup before training starts. So from there, I'm going to move to talk about some of the examples. And what you see here are 6 examples that we provide with Schola to basically demonstrate what it can do and how to use it. So the first one here is Maze Solver, where an agent using raycasts to observe its environment, which you can see visualized, basically solves a simple maze that's non-randomized. So it learns very quickly to follow the exact path and doesn't really do any exploration. And it moves by teleporting. It gets a reward for getting closer to the goal and a penalty for hitting the wall. So it tries to stay in the center of its channel. On number 2, we have 3D Ball, which is a pretty simple physics-based environment where an agent learns to balance a ball on top of itself. It can see kind of the ball's position and velocity, as well as control its own rotation to keep the ball balanced. And it gets a reward for every second it keeps the ball up and a penalty if it drops it. The next one is an environment we're calling Ball Shooter or Turret, where a rotating turret that fires projectiles has to hit targets that are randomly moving, so they jitter to make it a little bit more difficult. And the agent can see with raycasts fired out in a cone in front of it. So whenever it doesn't see any targets, it has to rotate to the next one to find it. Environment number 4 is tag, and this is a 3v1 game of tag where three taggers try and catch one runner inside a fairly big environment. I'm going to talk about this one in more depth shortly. The next one is basic, which is very simple. And an agent here can go forward to get a big reward or go backward to get a small reward, and it's just privy to its location. And then the last one is racetrack, where an agent tries to follow a racetrack. And it's given basically observations that tell it how fast it's going, where it is, and also its relation to the center of the track. And it is controlling the car via car controls. So you may notice that some of these are not exactly optimal, and that's because some of the videos and GIFs and other like imagery I'm going to show you in the upcoming slides is not necessarily from an environment that is completed training, as well as it may not be from the latest version, and they're just for demo purposes. So if you see some strange behavior, that is likely the cause. As you can see in the case of basic, it's pretty obvious to know that it should be going straight forward to the big reward, but it does not always do that. And one facet of RO training that causes this is called exploration, where if it always does what it knows, it thinks is the best, it'll never find a possibly better solution, right? So if it never tries, if it starts going to the small reward, it'll never actually find the big reward because it's not exploring. So you see, that's why it kind of goes in both directions to explore what's possible. So I'm going to show a bit of a longer video of the tag environment here before kind of digging into it a bit more and explaining exactly like what the observations are, how we set them up, what the reward is, the action space, and then showing some visualizations of those various parts. Right, so the blue agent is the one that's running, and it's trying to avoid the red ones that are working together. And then these are trained against each other at the same time. So they both learn, and this can lead to, in an ideal scenario, they kind of evolve together, but sometimes you can get a collapse where one of them starts to outperform the other one. And we often have to use what's called curriculum learning to resolve this, where we don't make it uniformly harder for both agents, right? We expedite one side of the game to make it easier, and then we kind of have to balance it out ourselves. Right, so this is tag, a very simple game. Runners win if they touch the blue agent wins if it hangs on. I'm going to talk about the rewards later slide in more detail. So to start with, what does the environment look like? The environment for tag is a pretty simple. It is a big room, effectively, with a few obstacles in it. We have these square obstacles in the corners and then 2 big circle ones. And agents are spawned randomly at the start of each episode and then have to, obviously the runner doesn't have to do anything, it just needs to hide, but the taggers try and find it. So this is pretty straightforward. Now I'm going to show a visualization of the observations, right? So the runner has these 360-degree raycasts, and it can tell whether an object is a tagger or if it's a wall, and it can also detects the distance when the ray hits it, right? On the other hand, the taggers have access to more position data, right? So they can see position, basically the relative positions of the other taggers as well as the runner, right? You can see this is visualized by these arrows here, with the red one pointing towards the target and the green ones pointing towards the allies. And they also have raycasts, but I've elected not to visualize those, as more raycasts turns this whole video into a bit of a soup. So you'll have to bear with me and visualize them yourself. Right, so that's what all the various agents can do in terms of seeing their environment. And then on the flip side, for the actions, we use a rather simple contraption here, which is that the agents can do left-right motion and forward motion. And how it works then is that the agent basically turns in the direction of the motion, right? So if it's receiving a combined kind of 45 degrees. So let's say we have 1 on the forward scale and 1 representing completely to the right on the left-right motion input. The agent is basically going to rotate itself to face 45 degrees to the right of its original position. So it's basically always facing in the direction it's going, barring for a few frames in between, right? And that's kind of visualized by these arrows. They're pretty much all exactly straight on, although one of the agents is very slightly off as it's currently in the process of turning. So then finally, for the reward setup, what we do is we give the taggers each minus 0.001 per step, right? That way they want to end the episode as quickly as possible, and there's no value for them to dilly-dally and kind of wait around. And then we have the runner. It receives a small reward, basically the equivalent reward as the taggers for just waiting out the end of the game. So every step it stays in, it gets a bonus. And then what we do is we add an extra penalty to try and avoid silly behavior where they hit a wall. Obviously, from the previous videos, it doesn't always pan out exactly that way, right? Because the agent can look at the future reward and think it's worth hitting this wall if it believes that it's going to get the big reward for catching the runner, right? If the tagger says, oh, I'll hit the wall for 3 seconds here and get a minus 0.03 penalty for 0.01 for each second, but I'll get a 1 reward, you know, if I catch the tagger, or sorry, if I catch the runner off of that, you know, the math looks pretty good. And then on the flip side, the runner gets a -1 penalty for hitting a wall. And generally, it avoids hitting the walls on its own just because there's not too much strategy for it to hit walls. As you know, it wants to be in open space so it can do evasive maneuvers. So looking at a few like top-down trajectory visualizations that we've kind of like picked, we can see an interesting one on the top left where the runner kind of likes where it's at, so it stays in the corner and waits. And we see it do this nice little circuit to basically run around the taggers, which don't actually get to it by the end of the episode, as it's kind of keeping away from them. And the top right, we can see a nice like chase where the one of the taggers is basically shadowing it, and then comes in to cut it off at the end of the episode, where the runner has to turn back and is then subsequently caught. You can see kind of the path of the tagger going up into the right, and then it loops back around here where these two come in and catch it because it had to avoid this one coming from that angle. And then a similar story for this one, right? The tagger kind of comes up, it sees this agent, it turns back, and then it's converged upon by the 2 other taggers trapping it. And then what I'm going to do here is I think that's what I want to cover for Schola. I'm going to turn it back to my colleague Mehdi to talk about digital twins and then wrap up the presentation.
Thanks, Alex. I guess by now, what we learned is, first of all, reinforcement learning is important. But the focus that actually we had up to this point, right, was on non-playable characters in video games. The question that I would like to answer here is, can we use whatever we provided to something that is not games, right? And to answer that, I would like to highlight 2 concepts here. The first one is the concept of basically robotics, right? In robotics, you have, let's say here we have an arm, and the arm is going to do something that is supposed to do. However, as you can imagine, it's really expensive to train these robots in practice. As we showed at the beginning of the training, everything is going to be so random. And for one particular robot to be able to act randomly, it's going to be very costly. The robot is going to get damaged, and then we need to replace the robot arm and everything, and it's so super expensive. To avoid that, there is a concept of making a digital twin, which basically means that you are going to replicate this robot. Let's assume that here a robot arm in a digital environment like Unreal Engine, and then try to teach the robot in digital twin and in basically this interactive environment to do what it's supposed to do. When everything is fine and you see actually the robot is acting not random anymore, but just moving the joints and everything perfectly, then you can go in basically real life and then use this sim to real transfer to achieve that. However, as you can imagine, as you move basically the robot trained in simulation to real scenarios, then you are going to face some challenges. It's not going to be perfect, and then you need to close this loop, going back to simulation, see actually what conditions your robot didn't see during the simulation, add that either with data generation, synthetic data generation, or creating some custom corner cases, and then train it better, and then come back. So this concept of basically digital twin and making something to works in simulation and then going back to real is something that we wanted to highlight. And the landscape is really vast, right? If you are interested in this concept of digital twin and robotics basically beyond non-playable characters in video games, there is a huge amount of literature and things that you can achieve here. With that, let me actually have this closing summary, and then we take some questions. So first of all, I would like to highlight the impact of the work, right? So AMD Schola is open source, and it's basically provided as a research, let's say, plugin or platform to facilitate the research that others are going to do. So we would like people to get their hands dirty, right, and start using AMD Schola to develop something big based on reinforcement learning and based on Unreal Engine. This is actually an open source project, as we said. So you can use this QR code to find basically the link that we release AMD Schola. And we have a lot of documentations about function calls and some examples that Alex provided, so you can see all those things. You can use AMD Schola for training non-playable characters in video games, or you can develop some digital twin version of a real scenario, let's say a robot or a car, and then you can start playing and improving that. As the last note, we are looking forward to seeing how you and the whole community is going to use AMD Schola to develop more advanced NPCs and digital twin. With that, I'm going to open the floor for questions.
Yeah, thank you. Thank you, Mehdi and Alex, for the presentation on reinforcement learning and the AMD framework to utilize that for NPCs and you mentioned at the end digital twins. We have one question at this point, and it's coming from Branimir Kovacevic. He's asking, are there any specific consideration while leveraging AMD Schola for AI-driven features in Unreal Engine when optimizing for AMD GPUs? So maybe I can just give a little bit of intro. So Unreal Engine is actually working on a, let's put it this way, common interface that helps to utilize all accelerators that are available in the system. And if you look into the AMD products, in discrete GPU, obviously you can utilize the GPU as accelerator for AI, and there is a special neural network interface or NNI that Unreal Engine is working on, and that's supposed to utilize GPUs, CPUs, or in case of some of the AMD products, APUs, which is CPU, GPU, and neural network engine integrated together. So those engines can be utilized as well. One of the things that I would like to ask you, Mehdi, is that to comment a little bit on cost of training for some of the use cases that we mentioned here in terms of what's the duration of the training and what is the cost of inference, what kind of recommendation you have in inference, especially when you have more than one non-playable character.
Sure. I guess for training, there is something that I would like to highlight first. So as you can imagine, you in reinforcement learning during the training, you have two two big components. One of them is the environment itself, and the other one is the agent, right? So agent, environment, and then agent is going to learn something during the training, and we call it, let's say, the brain or the model, right? Traditionally, in, let's say, supervised learning, we had this model sitting on the GPU, and because we could say that actually you have a lot of data, you already know the data, for example, in image recognition, you already know the data, right? And then you can batch the data, you can provide everything together to the for the inference or for the training to the GPU, then it was really fast, right? You know beforehand the inputs to the model. However, in reinforcement learning, the agent is going to interact, and then at each step, there is a new data, and you don't know beforehand. And because of that, this interaction is going to make the training complicated. Usually, people say that actually we have a CPU, which is the environment and agent, and a GPU, which is, let's say, a model, and they need to interact together. And it's going to basically we are going to be concerned about the communication overhead and all these things. Having said that, when the model is small, for example, if you have a few layers of multi-layer perceptron or feed-forward networks, in that case, usually it makes sense to just use everything on the CPU. As the model gets more complicated, let's assume that you have attentions and transformers and you have a camera sensors, right? In that case, when the model is big, training on the GPU can make sense, assuming that you don't do basically all these inference during the training, you don't that per frame, right? Sometimes you can just have this every few frames or every few steps, you do one function call, one inference call, right? There are some optimizations that you need to apply to be able to achieve a good performance during the training, but it's not rocket science, right? You can basically start simple, see actually what's going on, do some profiling, learn about it, and try to optimize that. So that's basically the general use case of training these models, right? For example, sometimes actually people add a lot of observations, but you really don't need that much observations, right? With minimal observations, sometimes actually you can achieve what you want to achieve with longer training. So there are basically a lot of parameters that as a scientist, you need to consider your inputs, your rewards, your observations, the actions that you take, the number of steps that you actually do one inference call. All these things are going to be important. Is there anything specific, Gabor, that you think I need to address or?
No, I think the conclusion here is that both training and, the training can be done on a typical desktop GPU quite successfully. So it doesn't require some kind of a data center environment. Sure. So the training is achievable within hours. Depends on a system and the complexity of the agent and the environment. And on the inference side, we already have behavioral trees running on a CPU, which is the current, what you call the AI-like, behavior that used for an NPC's control. I was speaking of that, a question for Alex. The traditionally games today still using the behavioral trees, which is more like a classic if-then-else algorithm. And then how you can compare behavior trees and reinforcement learning? What is the key difference in terms of an advantage of MPC trained by AI and reinforcement learning?
So I think one of the key advantages is also it kind of is the other side of the coin of one of the key disadvantages of RL, right? The advantage and disadvantage are both that it is unpredictable, right? You get an outcome that you maybe don't necessarily know going in. And this means that, you get stuff like the NPC walking into a wall, but on the other hand, it'll then be unexpectedly intelligent, right? And obviously the better the NPC is, the better it's trained, the more you just get the intelligence side and the less you get it being unpredictable in a weird way, right? Some of this is referred to as emergent gameplay, where like the NPC does things you don't expect or that feel kind of like a simulacrum of real life. But for like a behavioral tree, you can still achieve that effect, but oftentimes you have to do it by achieving an effect, right? Kind of figuring out shortcuts you can do to make it appear that way, or building a giant behavioral tree where you consider lots of options, right? And manually account for kind of all these contingencies to make the NPC look very intelligent, right? With reinforcement learning or like other kind of advanced AI based NPCs, that you can get that effect kind of by default. And I will say they're not necessarily, the approaches are not necessarily like at odds with each other, right? Because you can use reinforcement learning as part of a behavioral tree, right? There's no need to basically swap the whole system for one or the other, right? Your behavioral tree is a state machine where the leaf nodes of the tree represent actions or potentially like tasks, right? And those can be subbed out for reinforcement learning based solutions to those tasks fairly easily, right? So you can outsource some of it to reinforcement learning, some of it to the traditional algorithm, and get more power that way.
All right, so we are we are running out of time, and just a quick reminder that the website where AMD puts all the technologies for the documentation of public use has also the GitHub links that are part of this presentation. So the website is gpopen.com. You're going to find far more than AMD Schola. There's a lot of things related to the graphics and other engines. And it's a developer-friendly website. And with that, I would also like to thank you, HTEC, for this opportunity to present AMD Schola technologies. And thank you, everyone, for attending and for your attention.
Thank you for taking the time to prepare and deliver the presentation. It was a very engaging presentation, a very smooth delivery. I want to thank everyone who attended the presentation. And with that, I will close the 4th day of HTEC Days 2025 conference. Thank you all again.
Thank you, everyone.
Thank you.
Thank you.
Thank you.
Goodbye.